Good morning, this is Dr. Turner for Integrated Math 3. Today we're going to be looking at 8.5. 8.5 is going to be looking at using Pythagorean identities. That word should sound similar because we've done the same thing with Pythagorean Theorem. That should sound familiar. We've done that the last few years now. Pythagorean identities is based on the Pythagorean Theorem. I'm going to give you sort of a quick outline of what that looks like and where we get that from, and then we'll get into the actual examples. Don't freak out about the explanation. I'm not going to ask you to prove it anytime soon, but it's just where we get this formula that we're going to be using from. Okay, so let's go ahead and open that up. And here we go. Okay, so the idea behind the Pythagorean identity is based on what's known as the unit circle. Unit circle is something that we're going to be using a little bit more as we get into calculus next year and pre-calculus. But a unit circle is a circle that has a radius of 1. And the idea is, as I continue to draw a radius, here I have it drawn in this line here, I could draw the radius anywhere, right? Radius goes from the center of the circle to the outside. And using that radius, I can construct triangles inside of the circle. Inside of these triangles, of course, we have 3 sides. The radius has already been spoken for, 1, but the 2 sides we don't know. Now, we just got done covering in 8.4 and 8.3 and 8.2 that we can use triangles and our trig ratios to solve for missing sides, is the idea, right? So if I wanted to know the y value here, that would be opposite and hypotenuse in conjunction with this angle theta. So sine of that angle is y over 1. And cosine, with conjunction to this angle, would be adjacent over hypotenuse, so x over 1. Therefore, we can define sine and cosine as sine theta and cosine theta, respectively. Okay. Now, we know that the sides of a right triangle are related by Pythagorean theorem. Pythagorean theorem is a squared plus b squared equals c squared, where a and b are the 2 legs, in any order, and then c is the hypotenuse. So relating the sides of this triangle, where a is x, b is y, and c is 1, I have x squared plus y squared equals 1. We just got done defining x and y in terms of our trig ratio, so I'm going to substitute x for cosine, I'm going to substitute y for sine, and I'm left with cosine theta squared plus sine theta squared equals 1, and I'm just going to tweak how I write it a little bit here, and I'm going to write sine squared theta plus cosine squared theta equals 1. That's a notational thing. The reason we do that is to identify what is or what isn't being squared. In this case, we want to square the sine value, not square the angle. That's why we write the superscript 2 to the right of the sine instead of to the right of the angle. So it's a notational difference. We'll talk about it more in class, but that's why that's there. Okay, that's how we come up with this formula. What we want to do today is be able to use that formula to come up with answers to our trig problems. So, here a little bit. And usually I'm writing it as is, but just because it's a longer section, I sort of wrote it out beforehand. Okay, so bear with me as I'm going through. Start out in this section, you're going to be given a sine value, such as 3 over 5, and asked to find the opposite sign. So if I give you sine, you're looking for cosine. If I give you cosine, you're looking for sine. Now, here, you were given sine of 3/5, you're asked to find cosine theta. So to do that, okay, you're plugging in 3/5 into the formula, which we just identified down here, and you are solving for cosine. Imagine that cosine theta, like we defined here, is an x. If this was x squared, you would be treating it like any other problem, right? So for cosine, to solve this, first I'm going to evaluate 3/5 squared. Remember that a fraction squared, you square the top, square the bottom, so I get 9 over 25. Then I need to get cosine squared by itself. So I subtract 9 over 25 from 1, do a little bit of algebra here, and I end up with 16 over 25. From here, to solve the square root, the opposite is square. Sorry, the opposite square is square root. So the square root of 16 is 4, square root of 25 is 5. So my answer is plus or minus, remember that every square root has two answers, plus or minus 4 over 5. Now, we want to get used to using this theorem because that's the title of the section, right? Pythagorean identities. However, if you're given a simple enough fraction, like 3 over 5, you could just use Pythagorean theorem to solve this problem. So in part B, this is just showing the other way you could do it. If I gave you 3 over 5, what I would do is I would sketch out a right triangle, and I know sine is opposite over hypotenuse. So set up the right triangle and solve for the missing side. Okay. Using Pythagorean theorem, a squared plus b squared equals c squared. Now I need that missing side because cosine is adjacent over hypotenuse. So that's why we're doing that. So 3 squared is 9. 5 squared is 25. I'm going to subtract 9 from both sides. That gives me 16. And then take the square root, and we get plus or minus 4. So then I'll fill that in. Okay, there's my missing side. Now my cosine, adjacent over hypotenuse, is 4 over 5. So you can always do it both ways if the fraction is simple enough. 3 over 5, something like that. Now down here at the bottom in my notes, we've talked about Pythagorean triples before. Pythagorean triples are the sides that most commonly come up when you're dealing with right triangles. So, for instance, when I saw 3 and 5 in a problem involving a right triangle, I already knew that I was going to have 4 as the missing side because that's a triple. 3, 4, 5. If you know two numbers, you know the other number. Those triples are meant to be shortcuts, and the most common are multiples of 3, 4, 5, and multiples of 5, 12, 13. I would say 75% of standardized tests, you're going to see those numbers come up. But if you ever forget them, you can always just use the theorem and work it out. Okay. Now, example 2 is here as well for you if you'd like. But in example 3, I'm given a sign that is a decimal value. So here, using the Pythagorean theorem and doing it the triangle method is not really an option. There's a way you could get around it, but it gets messy. So here you're expected to be using the Pythagorean identity. So all you have to do is you're going to take your sign value, plug it in, so 0.132 quantity squared. You're going to subtract that from 1, and then take the square root. Now, of course, I didn't do all this in my head. You would be wanting to use a calculator, preferably Desmos, but it doesn't have to be. Okay? So, clear out my cache here. We had 0.132 squared. So I plug that in. I do 1 minus that value. And then take the square root. Now, I know a lot of you are still using your phone calculators. I would caution you, one, I would caution you to not round until the very end. And two, if you are rounding or need to round, remember my expectation is that you're rounding to 3 decimal places. So your answer here is 0.991. Number 4, start out with maybe a smaller number. Okay, plug in 0.5 for cosine. I want sine. So plug it into the identity. I have 0.5 squared. 0.5 squared is 0.25. Isolate your sine squared theta. 1 minus 0.25 is 0.75. And then you'll take the square root using your calculator. You end up with plus or minus 0.866. So even though the explanation up here might look a little daunting, the formula is just like using the Pythagorean theorem. Plug in what you know, solve for what you don't. That's it for today, guys. If you have any questions, please reach out to me. Otherwise, have a good day. I will talk to you soon. Bye.